So this is example number 1 for chapter 13. In fact, there's only going to be one example. This problem is extensive as it covers every single point of this chapter that is important. The thing to remember about this problem and many problems in this chapter is that although they are long and involved, they are not necessarily complicated or complex. They are just simply, again, long. There's very little in terms of trick or any sort of deception that could happen on the exam. The questions are usually straightforward. If you understand the mechanics, you should have no trouble at all with this question. In fact, it's a very easy question to pick up some points on. So let's get going. One caveat that I'll put out there at the beginning is I will not do this problem in the order as you can see here on this left-hand side. I'm going to mix it up a little bit, but essentially it's going to all end up being the same. So let's look at part A. It says the table on the right presents the average hourly outdoor temperature, X, in a city during a week and the city's natural gas consumption, Y, during the week for each of 8 weeks. The temperature readings are expressed in degrees Fahrenheit and the natural gas consumption are expressed in millions of cubic feet of natural gas, denoted as mmCF. The output, it's on the next page, of the data is obtained when Excel is used to fit the least squared line to the natural gas consumption data. So this is what the output looks like. I'll discuss this later. So essentially, we have a scenario where we would like to predict the natural gas consumption, and we'd like to use the average hourly temperature in Fahrenheit. So this is the Y and this is the X. This is the dependent variable and this is the independent variable. So part A says find the least square point estimates of B0 and B1 on the computer output in the next page and report their value, interpret, and then it asks some other questions. So I'm going to skip that part and I'm going to actually calculate B0 and B1, effectively calculate the regression equation. So usually you're going to be given a column for X and a column for Y. And this is where the tedious part comes in. I took the time to calculate X times Y, and I took the time to calculate X squared. And then at the end here, I have added all of them up. So this line is the summation of each column. So if you look at your notes, you'll recognize that it's to calculate the slope, you need what is called SSXX and SSXY. So the slope B1 is equal to SSXY divided by SSXX. SSXY is nothing more than the sum of X times Y minus the sum of X times the sum of Y divided by N. And the denominator is SSXX. It is the sum of the square of X minus the sum of X squared divided by N. And so this row here essentially gives you all those pieces that you need. So this could give you the slope of the line, B1. If you finish the math, you should get something along the lines of negative 0.1. And I'm going to round it. It's 1279, so I'm going to just say that it's negative 0.13. So once you have that, then you can calculate the intercept of the line. Nothing could be simpler. Y is equal to B0 plus B1, x1. Isolate B0. So you know this one already, but you don't know either one of these things. So what you do is you change the equation just a little bit. Make it as average y minus slope multiplied by the average x. So in this particular case, it's going to be B0 is equal to 81.7 divided by 8 minus a negative 0.1279 multiplied by 351.8 divided by 8. Why 8? Because we have 8 observations. So this should give you the intercept of the line. The intercept of the line is 15.84. So your regression equation is, well, let's write it in a thicker font. Y is equal to 15.84 minus 0.13 x. That is your regression equation. So that answers part A, number 1. Part 2, it says interpret B0 and B1. Let's start with B0, and this is B1. So when x is 0, the consumption of natural gas in the city is 15.84 million cubic feet of natural gas. Now, although this is the technically correct answer, you have to observe that none of the values that you used to get the equation is even close to 0. So you were only operating on the premise of looking at temperatures between 28 and 62 degrees. And so, to be completely correct, you never, ever, ever use an x value as an input into the equation that was not previously used in deriving that equation. So anything outside the range of between 28 to 62 degrees is going to be incorrect. And so in this case, although technically the answer is when x is 0, the consumption, so basically when Fahrenheit is 0, the consumption of natural gas in this city is 15.84 million cubic feet of natural gas. The correct answer is actually undetermined because 0 was not one of the values used to predict the equation or to derive the equation. So I'm just going to clean this up here, leaving the equation solid. Part 3, it says, is an average hourly temperature of 0 in the experimental region, and this is what we've just spoken about. It's not in the experimental region, and therefore using it to predict y is going to be incorrect. What does this say about the interpretation of B0? It means that it's dubious, meaning it's not accurate. Part B, use the fact that SSXY is equal to some value and SSXX is equal to some value. Y average is 10.21 and X average is 43.98 to hand calculate within rounding B0 and B1. So this is an example of what would happen on the exam. Instead of making you calculate the entire thing, we would set you up with the components and make sure that you understand how to use the equation. And so part B, it's already done. Part C, use the least squares line to compute a point estimate of the mean natural gas consumption for all weeks averaging hourly temperature of 40 degrees Fahrenheit, and compute a point prediction of the natural gas consumption for an individual week having an average hourly temperature of 40 degrees. This is somewhat of a trick question because they both use the same exact equation. It says use the least squares line to compute a point estimate for average hourly temperature of 40 degrees and for an individual week having an average hourly temperature of 40 degrees. In this case, both of them are going to be exactly the same. And so what you want to do is going to be y hat is equal to 15.84 minus 0.13, and you just enter 40 into the x and solve for that, and the answer to that should be somewhere along the lines of 10.72 mmcf, millions of cubic feet. Part D says calculate the coefficient of variation, calculate the correlation coefficient in total, if total variation is 25.54, SSE is equal to 2.568, and B1 is equal to negative 0.12792, which we've already determined in the previous part. So we're looking for the correlation coefficient. The correlation coefficient is rho. It is between 1 and -1. So I'm going to calculate R squared and then take the square root. So in simple linear regression, that's the only way to do it, or that's one of the ways to do it. And you can definitely do that. Take R squared and then take the square root of R squared to get R. So in order to get R squared is nothing more than SSR divided by SST. We don't have SSR, but what we do have is SST. SST we're told is 25.549. So if you subtract your SSE from that, you should get your SSR and then divided by your SST. So now that you do that, you'll see that R squared is going to be 0.8995. If you take the square root of 0.8995, you're going to get a 0.9484. So this is your correlation coefficient, but then you're missing the sign. It's important to note that the sign is the same sign as the slope. So in this case, it's going to be a negative 0.94, meaning it is a strong but negative relationship.